Hello and welcome to Easy Class for Me, and you can find our channel at www.youtube.com/easyclassforme, and this is a series regarding 8086 microprocessor, and this is particularly about the pin diagram of microprocessor. So in the previous video we have seen the architecture of microprocessor. So if you are not aware of this microprocessor architecture already, you need to see it because this will be used in the subsequent lectures and the current lecture also. So just to give you a brief up, we have seen the internal registers or the general purpose registers. We have seen the pointer registers which were associated with different segment registers which contain the base address of external memory. Then there was an instruction pointer, there was an adder which was used to generate the 20-bit physical address for the address bus by using these segment registers and the pointer register. We saw flag registers, we saw ALU, then we saw something which is called as instruction byte, then we saw the decoding unit and timing and control circuit. So this is how a microprocessor looks from inside, and we saw the structure of externally interfaced memory also, where we said that the externally interfaced memory is 1 megabyte and it is further divided into 4 segments of 64 kilobytes each, and those 4 segments performed independent operations of storing code, data, extra segment and stack segment. So these are the registers which hold the first address of that. So a lot of more things were discussed in that lecture, so before going to the current lecture you should see that also because that will be useful. So today's topic is the pin diagram. So I have made the pin diagram on the right hand side because all the associated things and tables will be shown here during the explanation. So we will begin by looking at what total number of pins a 8086 CPU or a 8086 integrated circuit has. Actually this 8086 is fabricated as an integrated circuit and it is provided in the market in the form of a 40 pin IC. So you can see here there are total 40 pins here, and each pin has got its own significance while making different operations. So today we will see the function of these pins, and one more thing, that 8086 can be used in 2 different modes. Means when we look at its integrated circuit, it has got 40 pins, and these 40 pins have different meaning in one sense and some different meaning in another sense. So here you can say that there are 2 things written, maximum mode and minimum mode. Minimum mode means when the processor 8086 is only a single processor in the complete circuit that we are using. So we call it as a single mode or minimum mode. And when multiple processors are used in the same circuit, then we call it as maximum mode. So maximum mode means there will be a parallel operation between different processors, and different processors will be performing different subtasks of a very big task. So in that case we call it as a maximum mode, and depending upon that you can see that inside small brackets whatever we have written is applicable for the minimum mode, and outside these small brackets whatever has been written is for the maximum mode. So these are the pins for which this bracket is given here. These are the pins which can be used either for maximum mode or for minimum mode. Rest all pins can be used in both of the modes. So what we are going to do is we will first start with the power supply. What type of power supply is needed for this 8086 microprocessor? So you can see that at pin number 40 you can supply VCC, which is plus 5 volt, and it can have a toleration of plus minus 10%. So a plus 5 volt DC supply is necessary, and here there are 2 ground connections. You can see them at pin number 1 and pin number 20. So there are 2 ground connections. What is the need for supplying 2 ground pins? Because 8086 it is having 40 pins, so it is a fairly big circuit. So since there are multiple sub circuits inside that, so to provide ground to all those circuits, while one ground is making its operation, we have 2 ground circuits here. And then now we saw that in 8086 microprocessor we had address bus of 20 bits and data bus of 16 bits. So to save the number of pins in the hardware, that is to manufacture the hardware in a cost effective manner, what they have done is they have time division multiplexed the address and data bus. So the advantage of time division multiplexing the address and data bus is that same pins can be used to transfer address also and data also. But since address bus is of 20 bits and the data bus is of 16 bits, that is why some of the pins of address bus will be left. So what they have done is, you can see here that here AD0 is written, which starts from pin number 16, and AD14 which goes to pin number 2, and then AD15. So from 0 to 15, there are a total of 16 pins which have combined address and data. A stands for address and D stands for data. So at one point of time they will be operating as address bus, and at another point of time they will be operating as data bus. So since from 0 to 16 or 0 to 15 there are a total of 16 pins, that is why data bus can be completely accommodated in that. But since address is of 20 bits, that is why we have A16, A17, A18 and A19. So these 4 pins are multiplexed with some status signals which we will come to very soon. But for the purposes of current discussion, address and data buses are multiplexed, and since they are different in size, therefore the lower order of address bus, that is starting from 0 to 15, are multiplexed with data, and the higher order data bus is multiplexed with something else which is called a status signal, and which we will come to very soon. Now, after having multiplexed these address buses, it might be the case that at particular time address is given and at some particular time the data is given. So since addresses are not given very frequently, means once you have specified the beginning of data segment from where you want to access data, or code segment from where you want to access your code, the address has been specified, and the next operations will be reading and writing into those memories or accessing data. So address is given once, and then there are multiple operations which have to be performed. So the bus will be used as data bus at that time. So to store the address that has been given on the address bus, we have something called as address latch enable. Address latch enable is a pin which will be set to a high value when an external device, which is called as a latch, or latch is also a form of register, which will take the address which is given by the address buses into itself and store it for its future use, because this microprocessor is employed in a system. So whenever address is given on these address buses, which starts from AD0 to AD19, a total of 20 number of pins, so that address has to be stored somewhere for future use, because in the next timing cycle this address and data bus will be used as data bus only. So to enable that, we have address latch enable. When this pin is set to high in minimum mode of operation, at that time the address from these pins will be collected into some different IC which is a latch, and we will come to the details of that when we will study the minimum mode. But just to give you a brief intro of how this functions, address is stored somewhere in the latch. So now after that, we have discussed these address and data buses which are multiplexed. We now come to these pins. This is the clock pulse which we have seen in the previous lecture. We require a 5 megahertz clock for 8086, although there are 3 different variants of 8086: 8086 itself, 80861 and 80862. 8086 uses 5 megahertz, 80861 uses your 10 megahertz, and 80862 uses your 8 megahertz clock. But for our purposes, since we are dealing with 8086 which has a 5 megahertz clock pulse with a duty cycle of 33%, so that input has to be provided at this clock pin. Now here we can see we have INTR and NMI. INTR stands for interrupt and NMI stands for non-maskable interrupts. These both are essentially same things. So INTR means whenever the processor is performing some task and you give it a new task to perform, so the processor will see if it is busy, it will tell that okay, I will not perform your task because I am busy, and if it is not busy, it will accept your interrupt request. Interrupt means it literally means that you are interrupting something or somebody to give him your task. So that is why this interrupt pin is used. And this NMI is also an interrupt, non-maskable interrupt. Masking means you are suppressing somebody. So maskable interrupts means whenever you give an interrupt request through this pin, then what happens is this processor has a right to do not have a right to deny your request, because it is non-maskable interrupt. It cannot be suppressed by the processor. However, this INTR pin, in this INTR pin, whatever interrupt you will give, depending upon the choice of the processor, whether it is performing a critical operation or not, it will deny or accept your request. So there is a difference between these two pins. Non-maskable interrupts cannot be neglected by the processor and they have to be served by it, but INTR pin, depending upon the status of what processor is doing, it can deny or accept your request. So on what factor does that depend? So that depend upon this S5 bit, means the address 18 pin is multiplexed, is time division multiplexed with this S5 pin, and this S5 pin indicates the status of one another flag which is called as interrupt flag, which we have not seen in the previous architecture because that is not usually shown in that diagram. So interrupt flag is also one of the flags which indicates that the processor is ready to take your interrupt request or not, and it is given by this pin number 36 in time division multiplex fashion. So if interrupt flag is set to 1, that is the value on this pin happens to be 1, in that case what happens is the processor will accept your request, or if it is set to 0, the request at INTR pin will be denied. But if it is given on NMI pin, that is the non-maskable interrupt pin, without bothering about the status of this S5, it has to serve the request. So this is the difference between these two NMI and INTR pins. So you can see on the left hand side we have seen almost all the pins from 1, which is ground, then from 2 to this 16th pin we have address and data bus, which is multiplex. Some portion of it is here also, and we have seen NMI, we have seen INTR, clock and ground. So the left hand side of this diagram is completely defined, and now we come to the right hand side. So for right hand side we have already discussed VCC, we have discussed AD15, we have discussed these address lines. Now we will discuss the meaning of these status bits which are multiplexed with the higher order address lines, 4 higher order address bits. So we will first come to this S3 and S4. Now in the architecture we have seen that when we had an externally interfaced memory of 1 megabyte, that externally interfaced memory contained 4 different segments of 64 kilobyte each. They were called as code segment, stack segment, extra segment and data segment. So when this microprocessor is accessing that memory, how will it indicate to the external world that I want to access one particular segment of memory? So for that purpose these S3 and S4 bits are used, and the way in which this processor will indicate to the external memory that I want to access your code segment or your data segment is shown here. In this, what will happen is, if the S4 bit and S3 bit has these particular combinations, then these particular segments will be accessed. Whenever S4 S3 is equal to 0, then ES or extra segment will be accessed, and similarly when these have these particular combinations, this particular segment will be accessed. So S3 and S4 bits indicate that what memory segment out of the complete 1 megabyte of memory are you trying to access. So this is an important thing to have. Now S5 indicates, as we have already discussed, interrupt flag. So if interrupt flag is set to 1, then microprocessor will accept your request at INTR, or if it is set to 0, then the microprocessor will not accept the request at INTR. But irrespective of the status of this interrupt flag at S5, NMI has to be always served. So this is what we have already seen. And then we come to S6. S6 is used for indicating, since we have internal buses inside the microprocessor, address bus and data bus. Similarly, when there is a complete big system, there might be external buses also to transfer data between microprocessor and memory and its peripherals. So there is something called as bus master, which controls the operation of external buses in combination with the internal buses. So if you want to give the control of the internal buses of 8086 microprocessor to the external bus controller, then for that purpose this S6 pin is used. So S6 pin, if it is set to 1, then in that case microprocessor gives its internal buses control to the external bus controller. So for that purposes it is used, and we will see relevant details of this when we come to the different complicated logic circuits which involves microprocessor and its interconnection to different peripherals. Now this S7 bit, as you see here, is a spare bit and it is not used for any purpose. It is just kept like that. And this BHE bar is a very important pin, and it is used for bus high enable. Bus means data bus. Since we are having a 16-bit data bus, so it can be divided into two parts: lower order bus, which starts from 0 to 7, and higher order bus pins, which starts from 8 to 15, a total of 16-bit data bus. So to enable the high portion or disable the high portion, this bus high enable pin is used. And as you can see, a bar is kept over this. So whenever the value of this BHE bar is equal to 0, when BHE bar is equal to 0, that means BHE is equal to 1. That is, this pin will be enabled when BHE bar will be equal to 0. So when I say BHE bar is activated, that means BHE bar has a value of 0, or equivalently BHE has a value of 1. So this has to be kept in mind. Now bus high enable is used in such a fashion that we have 16-bit data bus, and out of that the lower order address, the lower order bits from 0 to 7 are always activated when it is treated as a bus, but the higher order bits, that is from 8 to 15, they can be treated as bus or they can be treated as not as bus. So that depends upon BHE bar. When BHE bar is set to 1, that is BHE is set to 0, in that case the bus high enable is not enabled. Means when BHE bar is enabled, that means BHE bar will be having a value of 0, so BHE is having a value of 1. In that case the higher order bus will be enabled. Means from data bus pins D8 to D15, you can see it from here, that is AD8 to AD15. These are the higher order data buses. This is AD8 and this is AD15. So from these pins are already activated, 0 to 7. When this is treated as a data bus, then 0 to 7 are always treated as data bus. But at the time when we are talking about this AD8 to AD15, in that case BHE bar will determine whether these pins are treated as having some relevant data when the bus is treated as data bus. So when this BHE bar signal is equal to 0, that means BHE is equal to 1, that means bus high enable is activated. So in that case the higher order address bus or address and data bus multiplex will be treated as data bus only. So for that purposes we also have one table here. So before going to this table, we should keep in mind one general fact in 8086 microprocessor, that 8086 microprocessor is a 16-bit microprocessor, and frequently we will be able to transfer data of 16 bits from microprocessor to the memory or microprocessor to the peripherals, or in a reverse direction. So when we have externally interfaced memory and we want to access a 16-bit data in one cycle only, so for that purpose what we have to do is we have to access it from its even addresses. Memory has addresses from 0 to 2 raised to the power of 20 minus 1, and when we want to access the memory, we will either start from even address or odd address, because there are only two possibilities. So if we start from an even address, if we start accessing memory from an even address, then in one go we can access 2 consecutive bytes of the memory to have a 16-bit word which is transferred from the memory to the microprocessor, or in a reverse direction. But if you start from odd address, then for odd address there is a complication that you can access only 1 byte of the memory at one particular time. So now let us have a look at this. BHE bar is when bus high enabled is used for enabling or disabling the higher order bus, and A0 is the first bit of address, that is the 0th bit of address. So when A0 is 0, since it's a binary number, the complete address will be even, because if the binary equivalent of some number is such that the least significant bit is 0, then the number is even. So this A0, it can be obtained from this pin AD0. When it is treated as the address bus, then A0 will be available here. So when this A0 is equal to 0, in these two cases the address will be even, or otherwise the address will be odd. And I have just now told you that when you access this bus from this even address, you can access the complete word of 16 bits in one go. So you can see here, when bus high enable is activated, it has to be 0, because BHE will be 1 in that case, and A0 is 0, means you are treating the complete data bus of 16-bit as data bus. The lower bus is already activated, but this BHE bar tells you that higher order data bus is also treated as data bus, and in that case the complete bus is activated, the address is even, so whole word from and to even address can be used. Means suppose inside the microprocessor we are using BX register to have data from memory to itself, so whole word from and to at even address. So if we are beginning from the even address, which is indicated by A0, then inside the BX register we can transfer the data from BX to the memory, or take the data from memory to BX register. So that is what we mean by whole word from and to even address. So D0 to D15 will be used as data bus. In the second case, when we have bus high enable activated but the address is odd, and I said that when we access the memory from odd address, only one byte of it can be used. Complete 16 bits cannot be used, and since BHE bar is enabled, so since BHE bar is enabled, that is why we will be taking this upper byte from and to the odd address. So inside the odd address of memory, if some data is kept, that byte will be taken and it will be taken to the upper byte of the considered register. Suppose we are using BX register, so it has BH and BL two parts, and since we are dealing with only one byte now, so inside BH, that is the upper byte of that register, the data can be taken or given to this odd address. So this is what we mean by this. Similarly, when BHE is deactivated, that means now only D0 to D7 will be treated as your D0 to D7 will be treated as your data bus. So in that case, lower byte from and to even address can be transferred, and 11 stands for no operation. So this pin is very significant pin, BHE bar, and it is used with this A0 pin, that is when this address and data bus which is multiplexed is treated as address bus. So in that case, the status of this A0 pin and this BHE bar pin, it decides that how we are going to access the memory. So these points should be kept in mind. Now MN and MX stands for, now from here onwards, these pins are not multiplexed pins. These pins, they are the pins which have some different meaning in one case and some another meaning in other case. They are not time division multiplexed. In maximum or minimum mode, they have got different meanings. So if this pin has a value of 1, which means MN, or minimum mode has got a value of 1, so minimum mode is activated, and it indicates that this processor is operating in such an operation where only one CPU is there and other peripherals will be there. When the value of this pin is 0, which indicates MN is 0, so automatically MX bar becomes equal to 0 also, and MX becomes equal to 1. So when MX becomes equal to 1, maximum mode is activated, and inside maximum mode, the processors will be multiple. In the circuit, there will be multiple number of processors, and they will be operating combinedly to achieve a certain task. So the status 0 or 1 on this pin indicates the minimum mode or the maximum mode of operation. RD stands when this processor is reading something from the memory. So RD bar is also an active low signal. It is activated when the value of this RD bar is 1, or alternatively RD is equal to 1. So when the value on this pin is equal to 0, RD bar is activated, which means read becomes equal to 1. So for that purposes, when the microprocessor is reading something, it will indicate by activating this pin that I am reading something from the memory. Now the next pins that we are going to study, they have different functions in maximum and minimum mode. We already said what is maximum mode and minimum mode. So we will first of all discuss the minimum mode of operation, and then we will see what maximum mode means. Now in minimum mode of operation, let us begin by studying this hold function. Hold function, when it is an active high signal because there is no bar over it. So when hold is 1, so in that case what happens is, we have said that there is something called as external bus controller, and when we are using it in minimum mode, suppose some peripheral wants to use the address and data bus of microprocessor to transfer data. It might happen that some peripheral does not have a way to transfer data from itself to another peripheral, so it will be using the buses of the microprocessor only, the address and data buses of the microprocessor only. So in that case, to indicate that condition, this peripheral will set the value on this pin as high value. So a value of 1 will be set at that pin. So the microprocessor will see that there is a hold request, and what it will do is it will execute whatever it was doing, and it will, when it is completed with its execution, it will send a value of 1 at this pin, which means hold acknowledge. Hold acknowledge means you have at hold pin you have given a request of accessing the address bus and data bus of microprocessor. Microprocessor will complete its task, whatever it was doing, and then it will float a value of 1 on this pin, which will indicate to the peripheral that yes, your request has been accepted and you are now given a control of address and data bus. You do whatever you want to do with it, and then after doing it, you just make the value of that hold equal to 0, and this HLDA will again be taken back by the microprocessor, and microprocessor will be able to use its bus again. So hold is used for using the internal data bus and address bus of the microprocessor by some external devices. So this is the meaning of hold. It is different from interrupt. Interrupt is used for any general purpose task. It could be anything. It could be like you want to give it some different program, then that can be done through this interrupt and NMI pins. But hold is specifically for your address and data bus usage by external systems. Similarly, we have write bar pin, which is similar to read. If the microprocessor is writing something, it will indicate it on write bar pin by making its value equal to 0. That is, write bar equal to 0 means write is equal to 1. Similarly, we have memory or input output operation. Suppose microprocessor is dealing with memory in some case, so it will set the value of this pin equal to 1, and if it is not dealing with memory, it will set the value of this pin equal to 0, which will mean that memory is set to 0 but input output bar is set to 0 also, which means that input output is set to 1. Similarly, D stands for data, T and R stands for transmit and receive. So by now you have understood that if microprocessor is transmitting or receiving data, so correspondingly its pin will be set to 1 or 0 value. 1 value for transmitting and 0 value for receiving, because 1 value for transmitting will mean that the microprocessor is transmitting the data, and the value when it is made 0, so transmit becomes 0, R bar also becomes 0, so R becomes 1, so there will be reception of data from the peripherals to the microprocessor. DEN means data enable. Data enable means whenever you are transferring the data to a memory which is not employed as a one chunk of memory. There are several chips of memory. Suppose the externally interfaced memory is not 1 megabyte in one go. We have several different smaller chips. So to which chip the data should be transferred and to which peripheral the data should be transferred, so that chip or that pin is activated by data enable network. So at this pin, this DEN signal is usually given. Similarly, we have address latch enable, and we have seen the meaning of what address latch enable does is when address and data buses are multiplexed inside the microprocessor to save the total number of pins. So what will happen is address latch enable is used to store the address which is generated by the address bus externally into some register or a latch, so that it is available for future use. So we will see that ALE and DEN and these all pins are used combinedly in minimum mode, and how their operation is done when we will come to the topic of minimum and maximum mode separately, which is probably our next lecture, so you should see it there also. And INTA bar is used for acknowledging the interrupt. So if you make an interrupt request through this pin, then if your interrupt is accepted, which will be done when this pin number S5 is equal to 1. So if your interrupt is accepted, then microprocessor will float this pin in a low mode, because if INTA bar is equal to 0, which means INTA is equal to 1 and your interrupt has been accepted, and then microprocessor has stopped whatever it was doing, and now you can give it its new task. So this is used for acknowledging the interrupt in minimum mode. And we now begin with this reset pin. Reset pin is used to restart the microprocessor. Restart is the terminology that we use in current computers, and when we reset the microprocessor, it will direct the control of the instruction pointer to FFFF0 address, means 4 times F and 1 0. So there is a complete 20-bit address of FFFF0 in hexadecimal, and at that particular address the restarting instruction of this microprocessor is written, means whatever has to be done after restarting, it is the code for that is written starting from that address location. So FFFF0 is not a hard and fast address at which the restart program is written, but usually most of the manufacturers follow this practice. So that is why reset pin directs the control of this CS register and IP register to FF0, so that the microprocessor may restart, and the necessary instructions at the time of restarting should be executed from there. Similarly, this ready pin is used to synchronize this microprocessor with a slow device. For example, what happens is the memories that we have are usually not as fast as microprocessor. So when microprocessor is doing some task and it requires to have some data from the memory, or it requires to write the data to the memory, in that case the memory has to accept the data by the speed through which microprocessor is transferring it, if it is of the same speed. But if it is not of the same speed, it is not ready to accept the data at the speed at which the microprocessor gives it, so in that case the externally interfaced memory or the peripheral has to indicate this through a ready pin. Means whenever the device is ready to accept a byte of data, it will float this pin as high pin because it is an active high pin, and the microprocessor will know that now I can transfer data. Then after the transfer of data, this ready pin will be floated to low by the external device, so that the microprocessor will stop transferring the data and it will do its own operations. And then when the ready pin is set to 1 again by the external device, the microprocessor will again transmit the data. So in this way, this 8086 CPU is interfaced with higher or lower order speeds memory through this ready pin. So usually for the slower memories, because if the memory is slow, in that case only you need to use this ready pin. Similarly, there is this test pin. The meaning of this pin will be seen when we use the wait command. There is a wait command in the instruction set, so we will discuss this pin when we will discuss the programs for that. And now we come to the maximum mode pins. These maximum mode pins have the same meaning of these minimum mode pins also, but their terminology is a little bit different. And since there are multiple processors in the maximum mode, so to handle those requests, they have got some different nomenclature and different way of operation, but the functionalities are almost same. For example, the hold pins are called as request or grant. So if somebody or some processor in the maximum mode want to use this processor's address and data bus, then request and grant pins are used. They are same as hold pins of minimum modes, but this HLDA is not the request or grant acknowledgement. This is again a request or grant pin for another microprocessor, because when there are multiple microprocessors, so you need to have more than one hold pin. So these are two hold pins in the maximum mode, and priority is given to this. Means whenever there are two requests on these two pins, so the priority will be given to this and this will be neglected. So these are hold pins and there is no acknowledgement for these pins, right? So we will see there is acknowledgement, but not through this IC. It is through some externally interfaced devices, and that we will see when we come to the maximum mode of operation. Similarly, there is lock pin. When the microprocessor is doing some critical tasks, so it is not able to provide its address and data bus through these request grant pins. So this lock pin is used to indicate that microprocessor has locked its internal data and address buses and they are not made available to the external world for usage. Similarly, there are these pins S0, S1 and S2. So they are similar to memory input output, data transfer receive and DEN, but since we are using multiple microprocessors in the same system, so their usage is little bit different, and we will see it here. This S0, S1, S2, and these are their statuses, and this is the meaning of that. So when 000 is there is an interrupt acknowledge cycle. 001 is there, read input output port, write input output port, halt the system, then instruction fetch, read memory, write memory, and passing inactive. So the meaning of this will be clear when we will actually interface this microprocessor with some external circuit, and we will see it in maximum mode. But by now intuitively it is clear that when the meaning of the pin is 010, we are writing a input output port. We are not dealing with memory. So these are the meanings of these pins, and these are to be remembered by you. So S0, S1, S2 are seen. Now this QS0 and QS1, they stand for Q. We have seen that there is a queue of 6 bytes in the architecture of microprocessor, which is used to fetch instructions from the memory into itself, external memory into itself for execution purposes, and the parallel operation of execution unit and the bus interface unit was called as pipelining. So to indicate this status of Q, we use these two pins QS1 and QS0, and the meaning of these pins is like this. When QS1 and QS0 is 00, it means that in the last clock cycle no operation has been done on Q. When the meaning is 01, then the first byte of the instruction queue has been accessed in the last clock cycle. Means this QS0 and QS1 tells you the status of what happened one clock cycle before to the Q. So in the previous clock cycle, if Q was empty, it will be indicated by a status 1 and 0, and if it is 1 1, that means byte other than the first byte is used, which is called a subsequent byte. So this is about the status of this queue. And now we, depending upon the discussion for BHE bar and A0, we come to this diagram where we say that although we have already divided memory into 4 different segments, that was one view of observing the memory, but since we are able to access memory in such a way that we have odd addresses and even addresses, and depending upon the A0 bit, even and odd addresses are selected, so we can further logically divide this memory into two parts. One is called as the odd memory bank and other is called as the even memory bank. So all the even addresses are taken at one side and all the odd addresses are taken at one side, and we saw that by using this BHE bar and combination of A0 signal, this higher order bus was enabled. So BHE bar is given to D8 to D15, so as when this BHE bar is equal to 0, that is BHE is equal to 1, this complete thing will be enabled, or otherwise this is disabled. So depending upon this enabling or disabling, since odd addresses are kept as one side, so it will be convenient. So these even and odd address segregation of buses is also done there, and this is regarding to that your BHE bar and A0. So this completes almost all pins and the description of almost all pins, and the meaning of these pins, that is your maximum mode and minimum mode pins, will become more clear when we come to maximum mode and minimum mode in the coming lecture, which will be uploaded soon. So you should watch that also. So most of the pins are clear, and now we are also clear with the architecture. So I request you to visit our channel www.youtube.com/easyclass4me, and inside that channel there will be a playlist tab. Inside that playlist tab you should see that 8086 microprocessors playlist. So there all the videos will be available. Thank you for watching this.